Hi, I'm Peter Singer from the Centre for Human Values. It's my pleasure to introduce our third speaker in this series. And if you've been following the series, you have to admit we're not rigid about where we have the lectures. We've got to move around different buildings. So welcome to Geo for this one. And it's also my particular pleasure to be introducing Rob Socolow as our speaker, who's really been the driving force between organising this series of lectures. And that's very appropriate because he's working very directly in this field, in global carbon management, the hydrogen economy, fossil fuel sequestration. And the website says he's the co-principal investigator with Steve Picala of Princeton University's Carbon Mitigation Project, a $20 million 10-year project. I think that's now increased from what we learned on Monday. I don't know exactly how many millions it's been increased by, but some anyway, and it will go till 2015 now, is that right? So it's continued funding from BP, and Ford have also supported it. So this is a major scientific initiative to actually be doing something or find something practical that we can do about climate change. There's a lot on the website that Rob has done, a lot of publications. Probably the best known one is the 2004 article with Steve Picala called Stabilization Wedges, Solving the Climate Problem for the Next 50 Years with Current Technologies, published in Science, been very widely referred to and used in the Al Gore film about climate change, which means, just suggested to me, that in a way, just as our last week's speaker had some share of the Nobel Prize, since Al Gore won it for the film, we could claim some credit for Rob as well. It's a slight stretch, maybe, but we're very Nobel Prize conscious here at Princeton nowadays, particularly. So the other thing that I liked on the webpage, actually, that I wanted to read to you particularly, was that Rob was the recipient of the 2003 Leo Szilard Lectureship Award of the American Physical Society. And I mention that particularly because I like the citation. It says, "For leadership in establishing energy and environmental problems as legitimate research fields for physicists, and for demonstrating that these broadly defined problems can be addressed with the highest scientific standards." I think clearly that's exactly what we need to have done. And so I welcome Rob Socolow, and let me also say, after he finishes speaking, we'll have a brief comment from Bennett Foddy, who is the Harold Shapiro Postdoctoral Fellowship in Bioethics at the Centre for Human Values. Thank you.
Got it on. It's on. Is that okay? Yeah. Well, this is a wonderful series, and I'm glad to be honored to be part of it. Of course, once I said yes, they had to let me do it. But it's allowed me to pull together a lot of thoughts, directing them primarily at social scientists. I hope there's some in the room, and humanists who I'm trying to entice to think about the issues that we can take only so far, coming from the science and technology direction. The title has a word in it that I admit responsibility for. I coined it, Prospicience, the art and science of looking ahead. I think we need a new word to describe a new intellectual domain. In my own career, I have been passively watching one after another fundamental understanding from science about our past. The Big Bang was controversial when I was an undergraduate. The DNA was just also the paper of Watson and Crick was in that time period. The seafloor spreading, which happened in part in this building, was part of that time period. We have figured out so much looking backward. But we are pretty much flat-footed looking forward. And I'm going to give you several examples along the way here of how we are unsystematic and inconsistent as we think 50, 500, 5,000 years or longer. So prospicience is needed in infrastructure design, in natural resources, wilderness preservation, reinsurance, endowment management, and our understanding of what we are on Earth to do, as opposed to what on earth are we to do, what are we on Earth to do. I'll be talking in particular about two examples of this broad category of activity called geoengineering. On the left, you have an artist representation of how someday large amounts of this will be on the landscape. Air will blow in from one side, exit either up or out the other side, coming in with 400 parts per million of carbon dioxide and half of it removed and leaving with 200 parts per million of carbon dioxide, scrubbing the atmosphere with absorbers. Is that in our future? Maybe. On the right, you have a picture of a volcano, and as I'll be explaining, that imitating that volcano is the second idea, injecting particles on purpose into the stratosphere. We'll get back to both of those after a bit of a detour or a preamble. Why now? Why are these issues, these geoengineering issues, moving from almost, in some domains, taboo, in other domains, don't bother me? There are two reasons, and they're very different reasons. The first reason I call the hard slog problem. There are huge changes required to respond to the message the environmental scientists are giving us that we have to decarbonize the global economy. They will change entirely the way what our transport and power systems look like, how our buildings perform, and there will be winners and losers, and there will be deep challenges to equity, as I will explain. And it would be very nice to have some more options. The other reason is what people are calling the fat tail problem. Fat tail is of a distribution, which we think of as looking a little like a bell curve, except it's fat at one end, the high end, the dangerous end. Climate science cannot rule out extremely nasty outcomes of even moderate or modest increases in atmospheric CO2. And that has led people to believe that it would be irresponsible not to look for tools that could deal quickly with quickly developing emergencies. So what about the hard slog? Let me tell you a few numbers. The world is intrigued with a very tough goal for decarbonizing, for getting the world into a safer place, summarized by the phrase 2 degrees Celsius. What that means is that the global average surface temperature would never go higher than 2 degrees more than it was in the 17th, 18th century, the so-called pre-industrial climate, which was very stable. 2 degrees, but no more. Better, less. To do that requires global emissions per capita to be 2 tons of CO2 by mid-century and 1 ton of CO2 by the end of the century. And I will use tons of CO2 per person a number of times through this talk. The American average is 20 tons of CO2. The Europeans about 10. The world average is 4. China's about 4. It is not sufficient to limit the emissions in the prosperous parts of the world and allow the less fortunate to catch up. Such an outcome would overwhelm the planet. The emissions of the future rich must equal the emissions of today's poor, not the other way around. This is not happy news. It is not understood by a lot of people in ethics that this is the kind of problem we have. It is not a matter of just letting everyone imitate the well-to-do. To give you a sense of what 2 or 4 tons of CO2 is, let me relate it to ordinary activity. If your car gets 30 miles a gallon and you drive 10,000 miles in a year, you will have used your quota of the world average today, and you'll be double where we need to be in 50 years. If you fly, a mile of flying is about the same as a mile of driving in its carbon impact. If you heat a home in Princeton with natural gas, and it's an average home, reasonably well insulated, you'll put about that amount, 4 tons of CO2 a year, into the atmosphere. And if you're there sharing it with your wife, as I do, you can get 2 tons each. And for electricity, of course, that's the more complicated one because it depends on the carbon intensity of the electricity. If you're in Ohio and Indiana, where almost all the power comes from coal, you'd be allowed 300 kilowatt hours a month to use up this reference 4 tons of CO2. In New Jersey, it's about double that because we have a mix of natural gas, nuclear power, and coal. But your own electric bills, to the extent that any of you go home and check them out, are probably above 600 kilowatt hours a month. So it's not at all hard to use up the quota of 4 and to get to the U.S. average of 20 and to go higher still. This university has decided to focus on its own carbon. That means the emissions from our own cogeneration plant and our bought electricity from New Jersey's PSE&G and a few of our cars that run around, university vehicles that run around. That's all that's included, and that's 9 tons of CO2 a year from that source alone. So 4 is tough, 2 is tougher, 1 is very tough indeed. Never in history has the work of so few led to so much, being asked of so many. The so few, some of them are in this room, are climate scientists working on one portion or another of the impact of our species on this planet and how it works. I think there is actually one exception to this never is so few. I think the nuclear scientists working in the 1920s and 30s, culminating the discovery of fission in 1938, were a comparable group, small, self-contained, all over the world, and having deep insights that they had no expectation of having that are going to affect the way we live. There are some grounds for optimism, enough to keep me going, in 3 categories. The world today has a terribly inefficient energy system. Carbon emissions have just begun to be priced. Many of you know that in New Jersey there will be a price on carbon dioxide starting on January 1st of this coming year because of state policy and northeastern states' policy that is creating a carbon market for the emissions from power plants. And most of the 2058 physical plant is not yet built. We've had a number of discussions in the previous 2 talks about global equity. I want to make 2 points and make sure that people who think about global equity for this problem understand these 2 points. Climate change cannot be managed without the participation of the developing countries, on the one hand, and the carbon dioxide emissions of the global poor, 40% of the world's population, are negligible from the perspective of global warming. How can they both be true? Because there are wealthy people in developing countries and middle-class people in developing countries. There are about 4 times more people in developing countries than industrialized countries, if you define industrialized by the Organization for Economic Cooperation and Development. And they have about the same emissions as we do total, so their per capita emissions are 1/4 as high. And we have to keep both of those facts in mind. Here are the data about the OECD and the non-OECD emissions of carbon. The right-hand scale is in billions of tons of CO2. And you see that the OECD was overtaken by the non-OECD at about 2003. Those data go through 2005. And this is the statement that it's half developed and half developing country totals. And there has been, so that is important to understand. It's the important thing to understand. I have also done some addition for you to deal with a question called the legacy question in this subject. What have we put into the atmosphere in the past from various parts of the world? And the answer for the going all the way back to where the data really becomes significant, 1865, it's a 64-36 split, not 90-10, not 75-25. And Peter Singer made the suggestion at his own talk that we really should do the sum. We could alternatively do the sum, starting from our moments of evident cognition. We are aware of the problem for sure when we sign in 1992 the Rio Framework Convention on Climate Change. So since then, emissions have been surely from those who know the issue is there rather than those who did not know there was a problem in the first place. And that's a 50-50 relationship at the present time through 2005. Okay, so those are rather interesting data. This is a per capita y-axis versus population x-axis for carbon dioxide, and you see 2 views, 25 years apart. And I circled the number 10 tons of CO2 just to have you a number to look at. The U.S. indeed on the left hand is double that. China is the purple, and it is expected to double its emissions from 4 to 8 while growing. And the population, of course, is growing to the right. One of the things you see here is how much more important per capita growth is than population, although population is indeed 2 billion people higher in 2030 than in 25. And there are 2 other major developing country areas, This is the rest of Asia, Southeast Asia. India's in there. No, India's here. The rest of Southeast Asia is over. There are other large growth areas expected. So you see the message. We can't do without the developing countries. On the other hand, this is a representation that we've been working on, a number of us, for the last year and a half, thinking about the global population as the population of individuals emitting each a certain amount. And in a credible way, developing a view where the highest emitters are to the left, the lowest emitters are to the right, and all of the world's population of 6.1 billion people are lined up. When you do that, and we have ways of doing that using income distributions and assumptions about carbon to income ratios, there are 40% of that population has less than 1 ton of CO2 emission. Those are people living in villages without electricity, typically, very poor, all over the world, in Asia and Africa in particular, or they may be in cities in very primitive circumstances. Suppose we were to put a floor on emission of 1 ton of CO2. That extra region over here would be additional emissions, and it would be 1.3 additional billion tons of CO2 on 26, which is the total emissions in that year, 2003. So 5% more would allow what is actually emergence from abject poverty. The millennial goal vision of families with a modicum of well-being would in fact be people living with 1 ton of CO2 emission, and maybe even less than that. You would then have fossil fuels for cooking, canister of liquid petroleum gas. You would have transport with gasoline or diesel fuel by bus, car, or motorbike. And you would have electric power, produced in this instance with the average carbon intensity of electric power of the developing countries. That would add up to 0.5 ton of CO2, and people who study per year, and then people who study this have verified that you about double that to take care of indirect emissions. So this is a vision of, this is a message that is aimed in particular at a certain type of critique of the carbon problem, which says under no circumstances must we let the poor people start on carbon. We have to bring renewable energy to villages. Under no circumstances, it's the marijuana leads to heroin argument. We mustn't let them get near this stuff. It's completely wrong-headed. We do not need to solve the global carbon problem on the backs of the very poor. Okay, so what do we have around today? In 4 big categories for energy: efficiency, renewable power, nuclear power, and coal and biomass. And Steve Pacala and I laid out the view of a menu of a portfolio of options to be followed side by side and along many different lines at once. And our paper has contributed to some of this confusion, because in 2004, when we wrote it, there was a lot of defeatism. There was a general view that we did not have the tools to solve the climate problem. And what our paper did, it turned out it was arriving at a particular moment, was to change that. People realized that you could, indeed, tackle the carbon problem with the things we already knew how to do. But the second message was, these are very large changes. This is very tough, possible but tough. Psychologists in the room will know that possible but tough is not a place in which people's brains like to settle. So they change it, and they make it possible but easy. And so what has happened over the last 4 years, in my view, is that the second part of the message, this is really hard, don't pretend you can do it with a wave of the wand, has not fully come across. There is a view of this problem that it can be done by renewables and efficiency. And those people who argue this are usually actually arguing another point entirely. There is a preference that precedes the preference for solving climate change, which is why climate change I call a surrogate, of bringing the fossil fuel era to a close for whatever reason, curtailing consumerism and human-centeredness as opposed to being part of the larger family of life, promoting self-sufficiency as opposed to being dependent upon grids, diminishing the power of technical elites in favor of some kind of communitarian view, And for these advocates, climate change mitigation is not really the goal. And often, usually, it is, you have to scrape away the arguments to find this out. If renewables and efficiency were to suffice, that would be splendid. I personally don't think they do, if there is a sense of urgency. If we have to do anything like the kinds of targets we were talking about before, summarized by 2 degrees. Nuclear waste and nuclear and carbon capture and storage were the other 2 strategies, and they are both so confused in our understanding by this lack of systematic thinking about future time. It goes back 50 years, more than 50 years, the realization that radioactive particles, radioactive nuclei, had very specific half-lives that were probabilistic. And so if you held some plutonium-239 and you had a jar of it, you would know that there would be decays 50,000 years from now. In fact, that about a quarter of it would be around in 50,000 years, and it would be decaying. And if someone were to ingest some of that in that particular year, they had a fair chance of getting cancer. So we have this passage to the future embedded in the half-life concept, which I say has mesmerized the discussion. Because yes, it's true, but maybe that isn't the way to think about waste disposal. It has been the way to speak about waste disposal. In the meanwhile, that nuclear power plant in the bottom is in the distance because in the foreground is a finesse of the waste disposal problem called dry cask storage, which most of you have heard very little about. I think it should be celebrated because we're on the verge of getting into a desperate problem with our existing nuclear power plants of having waste building up dangerously on site and no ability to put them away in Yucca Mountain. And there was a finesse, a middle strategy was arrived at. Technology was developed. And it works for 100 years, at which point we'll have to go back and look at it again. Is that good enough? For it to be good enough, legally, we would have to renegotiate the social contract between the nuclear power industry and the public because irretrievable storage, put it away forever and no future generation would ever have to be burdened, was in fact the contract. We are now in the verge of putting something else away, carbon dioxide, deep below ground, and we are all, and one of the reasons I've been thinking about this is because I'm in that area, and there are no ground rules yet for how long CO2 should stay below ground. Is 100 years good enough? 500 years good enough? Are we trying to get the carbon dioxide to come out on the other end of some kind of fossil fuel era, at which point if we spread it out enough, it'll be relatively benign? It certainly is not like radioactive waste in that if it comes in, if it just dribbles into the atmosphere from some below ground formation, it will not do any harm at any time. But if too much of it goes in, obviously we're not getting any benefit. I'm not going to take you very far into any of these topics because I really want to move into the geoengineering. But to say that when you look at these 4 options, each has a dark side. Conservation has this regimentation dimension. I learned yesterday, I guess, that the Chinese now have a rule about the minimum temperature in a building, a public building or home at any given time of the summer. You cannot over air condition or you have a fine. We would have a hard time with that, I think, particularly in private homes. But that is an example of where aggressive conservation easily leads. Renewables, as we know so well now from our corn ethanol program, it quickly gets you into issues of competing uses of land. Nuclear power, I don't have time to discuss this, is deeply coupled to nuclear war. And most of us would not trade an attack on climate change for a nuclear war, even a small one. And clean coal bothers people for good reason related to what's called the upstream part of the problem. You can have a beautiful power plant capturing all the carbon dioxide you like, but if there's misery and environmental woe where the coal came from, you're not doing very well. So wouldn't it be nice to have a few more options? And I want to discuss first direct capture from air, where I have 3 informants who are deeply engaged in this work, all 3 of them brilliant, and I'll tell you a bit about them. So here's David Keith in 2005. He's actually the guy standing down here. Princeton tried to hire him, and he wouldn't come because he's a Canadian and he's loyal to Canada, and that's in Calgary. Maybe we didn't have Harold working hard enough at it. there is, all he is doing, and this is the very first beta, is to blow air through a spray of sodium hydroxide, and every 5 minutes he has a cycle, and he drops he observes that 20 parts per million out of 440 are removed from the carbon dioxide as it blows through this mist of sodium hydroxide, which makes sodium carbonate. So that's the idea, an absorber. Then you take the carbon dioxide that's hooked onto the sodium hydroxide and you drive it off elsewhere into a concentrated CO2 stream. So that's the idea. And of course, all three of those guys I mentioned are way past this and the kind of designs they're doing, the kinds of absorbers they're using. But the basic idea is blow the CO2 over something that wants it to take it in, and then concentrate the CO2, and then put it somewhere, like below ground, like the same places that the CO2 was going to for the coal technology. There are 4 different parallel efforts that I'm aware of. They're actually all being somewhat different. One is David Keith is using high temperature absorption and regeneration, meaning something like 800 degrees Celsius. And that's the tried and true. He just wants to see it working. Peter Eisenberger is playing around with solid amines that absorb and desorb at much lower temperatures and wondering whether you can use the rejected heat of power plants. Klaus Lackner has a proposal that nobody quite understands involving dry absorption and then amines that absorb when they're dry, and then when you add water, they actually reject the CO2 that they've absorbed. And then there are semi-biologically based approaches involving an enzyme called carbonic anhydrase, which greatly increases by factors of 1 million the rate at which CO2 can pass through a water boundary. And there will be a question of whether there's a place to put all the CO2 if you pull it out of the air. And notably, this can be done anywhere where there's a suitable formation, and so it may not be as competitive. Peter Eisenberger calls this says a short step from this is the global thermostat. You can tune the CO2 concentration. You can take it down below the pre-industrial concentration if you're so inclined. Obviously, this is big think. You can put the CO2 away. You can park it with a reversible storage instead of irreversible storage, retrievable rather than irretrievable, ECHO. And then you might be able to bring the CO2 out if you found yourself in a situation where you wanted the Earth to be warmer than it was in the verge of becoming. If you ask yourself how a global negotiation might take place with countries as different interests as they have today, it's pretty daunting. But I'm trying to tell you, this is where some of this is going. These are the kinds of things people are going to talk about. These are rich topics for what my friend Pakala calls brain candy. There is a moral hazard in this carbon capture and storage and from the air. If it certainly does compete with nuclear power, carbon capture and storage from coal, renewable energy, and so forth. If it could work, it should take its place. Traditional economic view, if you slot it in at its appropriate price, at the price of CO2 that makes it go. We don't know its price right now. We don't want to exaggerate how promising it is, and in the process, flag the efforts that are underway, courageous and bold efforts across the world to take carbon seriously and put in economic and incentives and drive technology in the direction of reducing the carbon emission. It will do that. Just the mere mention of it does that. It's political. It's born political, and that's a big challenge. Okay, on to the fat tail. The question that has been posed by the political process that started with the Rio Convention in 1992 is what concentration is dangerous? Because we were supposed to not allow the atmosphere to become dangerous. But nobody said how to think about that. And it's clear that thinking about that is even more complicated than people imagined in 1992. This is a report from conversations that many of us have had with climate scientists, facilitated in this campus by our being among so many climate scientists, both on campus and at the Geophysical Fluid Dynamics Lab. They cannot rule out the possibility that there is a great deal of feedback. Pacala's word is that the planet is very twitchy, and that small increases in concentrations can produce havoc, and that probability is not small. It doesn't converge nicely like the bell curve, as the bell curve does. Marty Weitzman, an economics professor at Harvard who's gotten very interested in this, has written several papers begging the environmental scientists to play with him and to figure out whether this is exactly the way to think about it. So far, he is persisting with one paper after another written for the lay audience or I should say for the science audience. Climate change at the fat tail, he says, threatens to drive all of planetary welfare to disastrously low levels in the most extreme scenarios. True or false, climate scientists? What do we mean by disastrous, is the phrase, disastrously low levels of welfare? Sea level rise is again the reference for many of us. These are 4 maps of the south of the Gulf Coast and Florida in the U.S. with 1, 2, 4, and 8 meters of sea level rise. The IPCC says that at the end of the 21st century, it will be 20 centimeters of sea level rise. But they say there may be some other possibility. And this next 5 years, there will be an enormous effort to understand the issues of the possible loss of ice from 2 particular places where it is miles thick. The Greenland ice sheet is worth 7 meters, and the West Antarctic ice sheet is worth 5 meters. When we came out of the last ice age, 100,000 years ago, it was 5 meters higher than today, as best people can tell. So we didn't quite finish the job this time around. And 8 meters is happening. This is the most complicated slide. Take some time with me to do it. At the right, we have Fatalia. Fatalia is, for the sake of argument, 6 degrees Celsius or more average temperature rise relative to pre-industrial. Do we live there? What you have are the distributions, flattened out, that are the best guesses for various concentrations of CO2 running from 0 to 6 degrees. And the concentrations are 100 ppm apart, except the top one. And the middle one is double the pre-industrial concentration, often the reference concentration for discussions. And we are told that 2/3 of the time, it will, the best we know, it will be between 2 and 4.5 degrees, possibly lower, but not much, possibly higher. And similarly for the other concentration. The reason this slide is so important is because it is evident that this is summarizing how much we don't know. The science community does not know at this time, and I can also report it is not learning quickly. These uncertainties are not shrinking at all over several decades. And it is truly important to present the climate problem to the public, to the decision makers, as a matter of buying insurance, managing risk. The business folk get it immediately when you explain it to them. But they may not have heard it that way. The worst and best outcomes compatible with today's science are entirely different. There is no line in the sand with safety on one side and disaster on the other. I mean, I have the opportunity now to advise 2 different museums about global warming exhibits, and I want them to show this, sort of at the same concentration. It might look like this, it might look like that. 2 sides of a cabinet. It's not the way people are thinking about it right now. It is harder to understand or to put into one sentence than, don't do this, don't do that. Can we not know whether we live in Fatalia? I'm trying to see how many people from GFDL are in the room right now. Oh, we've got 2 over there. And I see a few people who are in the AOS program. And I try to say this every time I'm with them. Havoc studies are a priority, and they are a challenge to the climate research community. And why can't we answer this question better? If I ask people, there's a famous negotiation that this is parallel to. Do we know for sure that the climate sensitivity is less than 20 degrees C? Well, if so, by what reasoning, and why doesn't it apply to 10, and why doesn't it apply to 5? What could we measure? What active experiment? But we do not know. And so we must assume that we do live in Fatalia and that we could find out via sudden change. And that motivates the search for fast geoengineering matched with the sudden onset of a crisis. Mount Pinatubo, the largest, going back in time, it was the biggest explosion. Nothing as large as that has happened since then. Cooled the planet by 0.5 degrees Celsius 6 months after the explosion, after which it started to recover. And 10 million tons of sulfur was injected into the stratosphere, which reflects sunlight. We think we understand what's going on. Less, it was dimmer on the planet. Sunlight was reflected, and a lot of things changed. There's a lot of signals in various environmental databases. So if you put particles in the stratosphere, you reflect sunlight and things cool down. So maybe we should be ready to do that. Should we be ready to do that? The idea is to match it to emergencies because it is fast. Faster than trying to cut emissions if something suddenly shows up that we didn't expect. They have even if we could do it quickly, the effect would be slow. So the response is, so the first feature is it's fast. The analogy I think is best, at least it's working for me, is epinephrine, which is if someone has a terrible allergic reaction, if you can get them epinephrine into them, you can save their lives. They've eaten something on peanut for some people, a bee sting for others. And so every doctor has epinephrine in his medicine cabinet, or her medicine cabinet. But James Lovelock, who's a famous guy in this field, says, well, this is, but geoengineering right now is 19th century medicine. I think that's a very good phrase. Well, I was part of a summer study for a week in Santa Barbara this summer, which was trying to ask, well, if you had a research program to develop this epinephrine, what would that research program look like? And we're going to come out with our report in a month or so. It was chaired by Steve Koonin, whom some of you know, who was the chief scientist at BP, actually, former provost at Caltech, and who likes running studies. He's very good at it. And we were looking at issues like how do you actually get the particles into the stratosphere? And it turns out they tend to clump, and then they would fall out quickly. And the questions of whether there's some side effects we already know about that are really nasty. And one of them is that it tends to deplete, certain particles will deplete the ozone layer in the stratosphere, the very ozone layer we've been trying to protect. So those are serious issues. But a more serious issue, or at least a conceptually fascinating issue, is what I'm calling rapid disengagement. Suppose for one reason or another you've been putting particles in the stratosphere to cancel the carbon dioxide you've got there, and maybe that you're continuing to put there. And then for some reason you need to stop. You might need to stop because of, on purpose, you want to stop because you've discovered a side effect that you didn't know about, or you might have political failure. You've been injecting this stuff year in and year out for a long period of time, and then there's a revolution or something like that happens, and you don't have or huge financial crisis, and you don't, that's impossible, and you don't have the ability to do this. So here is a modeling effort that actually shows a pretty interesting story. It's really a little wild, but fossil fuels do not die out until we've used all kinds of unconventional fossil fuels. We've burned all the way through to 2300. We're still going strong. The peak is 3 times what it is today, about a century and a half from now. And if we do nothing, the red line on the bottom shows that the carbon dioxide merrily rises to 7 degrees Celsius above the present. That's the red line. Suppose instead that we decide we have a goal of not letting it go above 2 degrees. Then just as it's about to hit 2 degrees, we start injecting sulfur in 2170. That's the blue line in the middle. And with injection that is comparable to the injection at Pinatubo, but year in and year out, we manage to keep the temperature locked at 2 degrees Celsius. This is a caricature of what we're talking about, but it's not misleading. Okay? Then the authors of this paper, use the phrase, well, this is really a sword of Damocles. The concentration I think I understand this particular point. At some point in roughly 2300, there's a crisis. And and the concentration in the atmosphere is 1,852 ppm. I was trying to think that is right. But there's enough sulfur in there to keep the temperature 2 degrees C. But then the injection of sulfur, which is what's shown there, is interrupted, and it follows the middle picture, plummets to 0. What does the temperature do? It, opposite of plummets, it spurts to by several degrees Celsius as soon as you stop. This is not user-friendly. As a consequence of the interruption of injection, quote from this paper, within a few decades, winter warming in the polar regions exceeds 10 degrees Celsius relative to where it started, and summer warming in the northern temperature latitudes would be about 6 degrees Celsius. Then they continue, coming generations will have to live with the danger of this sort of Damocles scenario, the abruptness of which has no precedent in the geological history of climate. Now, here's an interesting one. Do we want to go down that road? Well, do we want to go down that road? The more we fear climate change, the less we can allow ourselves to be squeamish about imperfect solutions. We must remember that we want solutions to work. It can't be enough to identify what's wrong with the strategy as it is first proposed. We must ask, with what changes would the strategy become acceptable? How might we get from here to there? In this case, perhaps a smaller loading of sulfur could buy off a couple of decades of global warming and reduce things. Would we want to live with a spurt that would happen if we weren't able to continue that? 2 million tons of sulfur instead of 7 or 8 would offset 50 parts per million, is my estimate. And we might be able to sheathe the sword by combining air capture with sulfate injection. We pull the CO2 out of the air, and at the same time, we're putting some sulfate up there. So we don't have the sort of damage. That's an engineering response to the moral question. But we also have to talk about getting to know. Now, we may decide in some situations to forego an option, and this may be the result of a moral judgment. We will prefer enduring some amount of climate change to the compromises required to avoid it. A few more slides. Toward what ends will we use geoengineering? Suppose, for the sake of argument, that we get smart enough and feel as we've done some experiments, we feel we know what we're doing, and we actually can geoengineer the planet. We've decided that we understand the risks and that they're tolerable rather relative to what would happen otherwise. That these problems of choosing a climate, choosing a temperature, turn out to be negotiable. We do actually arrive at a consensus that we would like the planet to look like this and not look like that. Then how will geoengineering, because those are obviously not big things to concede at this moment, but concede them and ask the question, toward what end? Genetic disease was the motivator of genetic engineering, and the resultant tools now allow enhancement of the human species, prettier, taller, smarter. Geoengineering is being motivated by the prospect of horrible climate change, but its tools will allow the enhancement of the planet. I think in particular the moderation of extreme events. Warmer winters, where people want them, cooler summers where people want them, less severe storms and droughts. A geoengineered world bears almost no resemblance to the world desired by environmentalists who seek to reduce the influence of human beings on other species and ecosystems. We are basically saying, this is how we want it, and we'll set it up that way. On the right is a wonderful short book by Michael Sandel called The Case Against Perfection. He's a philosopher, actually a political philosopher at Harvard, and continuing the metaphors of medicine, he is asking about the question of perfecting the species. And he's intrigued with the moral ambiguities associated with sex selection, eugenics, steroids in sports, cosmetic surgery, hyperparenting, which I think some of the people in this room could identify with. He argues that enhancement can be pursued to excess. He sees a loss of the ability to savor the life we have been gifted. He talks about the giftedness of what we start with. He sees value in randomness and the unbidden. And he says, when science moves faster than moral understanding as it does today, men and women struggle to articulate their unease. So I think I hope we'll discuss this in the question and answer period. might we overdo it in finding a planet just the way that is just suitable to ourselves, take out its randomness and manipulate it through and through? A happier note. I'm intrigued with the way in which people who work in this field, myself included, develop a planetary identity. We augment our previous loyalties to family, to tribe, and to a nested set of political entities from the village to the nation. Every man's death diminishes us. And we develop loyalties to future generations. What changes when there are lots of people who have these norms? Might one consequence be strengthened efforts to address global poverty and world peace, negating the claim that climate change is a distraction from assignments of greater urgency? The strongest arguments that I encounter against dealing with global warming is that we have more important things to do, under the assumption that those can't be done at the same time, notably dealing with world peace, nuclear war, bioterrorism on the one hand, and global poverty on the other. But it's not clear to me that these don't come together via a planetary identity. But finally, getting back to prospicience, we have scarcely begun to ask, what are we on this planet to do? What are our goals and what are our responsibilities? Imagine spending as much effort on a collective destiny on Earth as we spend on our personal identity, our personal destiny in the afterlife. Thank you. Bennett Foddy has been a wonderful interlocutor as I've been developing this talk. I'm very eager to hear what he has to say.
All right. Well, first of all, I'd like to thank Rob for his talk. I think it was a really strong, practical case for taking geoengineering seriously. I should start by saying I'm not a scientist and I'm not a specialist in the area of climate change. And a lot of the ethics, which I take to be, a lot of the ethics of this issue, which I take to be the question of what we should and shouldn't do, is going to be determined by the practical science, which is to say what will work, what won't work, what are the relative risks, and when is a given science ready to be used. I think even the moral hazard argument that Rob touched on, the idea that we only have enough effort for reducing carbon emissions and not for also geoengineering, that's also an empirical claim, a psychological claim in this case, about what people can and can't do. And so, I mean, I think science has a lot to say about the ethics in this. But not all of the arguments against geoengineering can be solved or answered empirically. Some of them require a kind of a philosophical, analytic approach. So I'm going to try to give one example of a dimension of this problem that has a more of a kind of a philosophical solution. Okay, so in Peter Singer's seminar 2 weeks ago, he mentioned George Bush's claim that the USA shouldn't be expected to act unilaterally or, if you like, altruistically to reduce carbon emissions. And I think the mood in the room, what we mostly agreed is that, in fact, it would be okay, at least, or it would be good if the USA did, in fact, act unilaterally to reduce emissions. And then last week, we had a talk by Richard Somerville, who said that the USA had no right to act unilaterally to use geoengineering to remove carbon from the atmosphere. So I was curious about that, and why is there this distinction between geoengineering the carbon out of the atmosphere and just not putting it there in the first place? Well, one of the reasons might be that we just think it's riskier to employ geoengineering than to reduce emissions. I mean, that would be fine. But what Rob was arguing today, what I take it to mean is that it's if we settle for just limiting or even just entirely eliminating our current carbon emissions, that's not going to be sufficient to completely eliminate the risk of a catastrophic climate change. So no matter what else we do, we're going to have to reduce emissions by a lot, by quite a large degree. So the question isn't really do we geoengineer or do we reduce emissions? It's really do we geoengineer? Do we geoengineer in addition to reducing emissions? So both options, which is to say geoengineering and not geoengineering, might bring about a catastrophe. So it's a question of whether the catastrophe is caused by the geoengineering technologies or by a failure to geoengineer. So this bears a certain similarity to a lot of problems that we look at in my field of bioethics, most frequently in medicine or in biological science. And these arguments appeal to the idea that there is a moral asymmetry between bringing about a consequence by action or bringing about the same consequence by inaction. So the most basic example of that is the idea that there is a moral difference between killing somebody and merely letting them die. So Peter Singer has argued in a number of places that there's no difference between killing somebody and allowing them to die. But I think maybe the majority of lay people and also a number of well-respected philosophers have certainly argued for the reverse, that there is, in fact, an important moral difference between killing people and letting them die. This asymmetry is also often demonstrated using a hypothetical case, which we call the trolley problem. So in the trolley problem, there is a trolley is out of control, and it's heading down some rails towards 5 people. It's going to crush and kill them. And you have the choice of whether or not to throw a switch. And if you throw a switch, the trolley will go onto a different track and hit 1 person instead of 5. So a lot of people think it would be wrong to throw the switch, even though fewer people will die if you do than if you don't. So in other words, to take action can be worse than to do nothing, to omit that action, even though the consequences would be better if you acted than failed to act. All right, I'll give one more example of this kind of asymmetry argument. Francis Fukuyama, when he was writing about the enhancement of humans rather than the enhancement of the environment, appealed to what he called the precautionary principle. The precautionary principle just says that when you're considering employing some kind of new technology, you shouldn't employ it unless you're sure that the risks are negligible or zero. And he says, furthermore, that this principle indicates that the burden of proof for showing that there are minimal risks falls on the people who want to act, not on the people who don't want to act. The only reason that you would put the burden of proof that way is if you think that there is a moral asymmetry between action and inaction. All right, so not everybody believes in this distinction between actions and omissions, but many people do, if not most, and I think it comes up again and again in the kinds of arguments that people give against geoengineering. So these arguments take the form of saying things like geoengineering would be arrogant, or it would display hubris, or that we'd be playing God. I mean, that's an argument that you can make in both a religious and a secular way. Last week, Richard Somerville said, no, nobody has a moral right to geoengineer the climate. And he said we should try to beware of unintended consequences. And I think all of those sorts of claims demonstrate this belief that it's worse to be responsible for a catastrophe of your own making than a catastrophe that you merely allowed to happen. They're all examples of this distinction between acts and omissions. But I think even if you believe that this distinction is real, even if you think that there is a distinction between acts and omissions in these traditional cases, like in the trolley problem, you shouldn't believe in it in the case of geoengineering. I'm going to just give a couple of quick arguments for that. The first one is, no matter how we get to a climate catastrophe, whether it's by geoengineering or by not geoengineering, it's going to be as a result of our own actions. So either we'll have a catastrophe that was brought about as some kind of unforeseen consequence of a geoengineering technology, or it will be a catastrophe that came about because we continued for a better part of a century to put huge amounts of carbon dioxide into the air, and then we didn't do enough to reverse it. So in one sense, you could say, I mean, it's just as arrogant to assume that we can get away without geoengineering as it is to employ it. So it's somewhat like the trolley problem that I mentioned, except in this case we're also responsible for having started the trolley towards the 5 people. And I think most people would agree this changes the moral dynamics of that case. The second reason I don't think that you should believe in the act-emission distinction in this case is that we're dealing with a shared resource, which is the atmosphere in this case. So Richard Somerville mentioned last week as a justification for the idea that we should beware of geoengineering, he said, this is similar to medicine. He said we should consider the do no harm principle in medicine, which is a principle that prohibits doctors from using risky or harmful treatments on their patients. So thinking about it, do no harm really comes in 2 flavors. The first flavor is one which just tells a doctor not to accept unnecessary risks, not to enact a treatment which is unnecessarily risky. Now, I agree with that principle as it's applied to geoengineering. I think, if it turns out that carbon scrubbing or sulfur injection is too risky, I mean, it's quite clear that we shouldn't employ it. The other flavor of do no harm, though, is a principle of distribution. Now, principle of distribution, when we're talking about it in bioethics, we usually consider this case called the transplant case. Now, in the transplant case, you have a surgeon who is performing a surgery on an unconscious patient, and he realizes that without anybody knowing, he can kill the patient on the table, take all his organs, and save the lives of 5 other patients. Most of us take it to be unjust for the doctor to do that. Even though more people will be saved if he goes ahead and does this, we think it's unjust to harm one person in order to benefit another, or to harm one group in order to benefit another. That's a principle of distribution. Now, I think if geoengineering was a distribution problem like the transplant case, then it might explain why we think that it would be unjust for the USA to unilaterally employ geoengineering. But it's not a distribution problem. You're not harming one group to benefit another. You're risking harms to everybody in order to benefit everybody. It's a shared resource in the case of both of the technologies that Rob was talking about, carbon scrubbing and sulfur injection. And I think that means that the principle of distribution doesn't apply. So I should reiterate here, I think that the empirical assessments of risk and of benefit supervene on these philosophical concerns. If it turns out that these technologies are too risky, I think it's quite clear that we shouldn't employ them, or we should wait until we can reduce the risks. Clearly, there's a spectrum of cases. Okay, so there will be cases where nothing good can happen if you fail to geoengineer. So the case that I could think of is, suppose an enormous meteorite is heading towards the planet, and it's going to wipe out all life on the planet, and we know that if we fail to act, a large proportion of the life on the planet will die. And in that case, nobody would say that it's better not to act than to act. And then in the reverse extreme, there are cases where bad things can only happen if you employ geoengineering, where the status quo is perfectly safe and perfectly okay. So I think it's clear that geoengineering falls somewhere between those 2 extremes. It might be worse to geoengineer than to not geoengineer, or the reverse might be true. So what do we do about these cases? Well, we try to weigh and discover the actual risks. We try to figure out which of these extremes it's closer to, and we make our decisions based on a kind of a prudential analysis. But we need to be careful that we don't give any additional weight to the idea that actions are worse than omissions. I mean, I'll just finish by responding to that quote of Sandel's that Rob brought up, the idea that we should be open to the unbidden. Well, I think by the same token, we need to be open to the forbidden. Thanks.
Thank you to both speakers. I think we've had a really good union of the science and the humanities here. So we're open to questions to either or comments. Yes, Darryl.
Bennett Foddy.
And that was kind of something like the idea that there is kind of collective property right. That could also explain the kinds of objections you might have in climate as well as property. There's something like a collective property right that one group of people to make a change that are not violent. Again, who knows whether this is actually the view we have in mind, but I'm wondering if a view like that is something that bears.
Right. Is this doing anything, this microphone? Yeah. All right. Yeah, I think that's right. I mean, that could be what he had in mind, except he was raising this do no harm principle as the form of the argument, and I mean I can't agree with it in those terms. It's quite a bit more of a complicated discussion you have to have if you're going to talk about collective property, and that's certainly I don't think it automatically falls down in favour of failing to geoengineer, though.
First, I want to thank Bennett for his comments and for linking this to the active-passive intervention issue, which I think is brilliant and probably will lead us further. One thing I wanted to slightly disagree with, and it relates to your question, is that this problem is distributional in the sense that a change in the climate will benefit some and damage others. Canada and Russia are not so displeased with global warming. And so it is a common property. The usual language is that the atmosphere is a commons, as the ocean is and other treasures are, and so it is the question. Management of the commons is a political problem. There's a law of the sea. There are some laws about what can be done in the atmosphere, and so forth. I wanted to say one other thing, but I'm not. Oh, but so there is a whole burgeoning literature that puts this into our trendy subject of terrorism and unilateral action. That a country will, how should we manage it if, in fact, a single country decides to geoengineer something to its benefit when others don't want them to? And I think that may be part of what was in your question.
Can I just add one? I mean, I agree with that. Of course, one of the things you can point out is that most people, as I said, most people are not too worried about having one country unilaterally decide to reduce emissions. But arguably, that's not good for Russia and Canada. It might be good for Russia and Canada. Who knows? I mean, who knows how catastrophic in the end the results might be. But if the results aren't catastrophic, if it's just an incremental increase in temperature, it might be good for parts of Canada and Russia if the global temperature increases, in which case it's bad for them if we stop emitting carbon. So these kinds of arguments do seem to apply to both sides of this.
I'm just going to add one thing to that, and that is, as well as the active emissions distinction, there may be a natural-unnatural distinction going on here, because that's often very powerful in people's thinking. And the example you gave might say, well, okay, it's fine for nations to reduce their emissions outputs because that was an unnatural warming. The situation would have been different if we discovered that the planet was warming because of the natural release of some gases from somewhere or other. Would we then have had the right to do anything about it, even if the consequences might have been exactly the same? as the current consequences from anthropogenic climate. Yes, there.
Yes, okay. So there are people who know more about this than I, but the aerosols are absolutely critical in understanding why we don't know how twitchy the planet is, because it is the cancellations that are occurring from the aerosols side by side with the greenhouse gases that are creating some of the considerable amount of the complexity, including because the aerosols have a critical role in the formation of clouds, and clouds are the hardest part of the modeling problem as best I can understand. Similarly, one can imagine, and I wish we would work harder at trying to imagine, deliberate manipulation of aerosols to learn about how the planet works. Shutting down power plants for a week globally for the value it would teach us, for example, things of that sort. Okay, so yes, and in some sense, what we're talking about is if we're going to reduce aerosols as we are increasing greenhouse gases, as we have more pollution control. A lot of the aerosols are related to conventional pollution, and as we spread around the world environmental controls, the aerosol loading of the planet will go down, and and the amount of cancellation will gradually be revealed, and we will find out something about these feedbacks that we're so concerned about. But there are some environmental scientists, Jeff and Bess and others around. Any one of them want to add to that? Right. If we shut it down, they fall out of the atmosphere, just as that's the argument why they can get an effect quickly up or down. Right. And a good trade.
Okay, thank you. Yes.
Rob, can you say a little bit more about
Say more around what?
It seems to me that to avoid this problem of a sudden turn-off of the aerosol, you're simply storing the carbon or emitting gravity. So you would prefer your
First mechanism is certainly working within the system that we know. I'm going to be organizing a study of direct capture of air over the next year or so with the American Physical Society to get something much more available out there. The people working in this field are at the moment working pretty much independently. It is promising, and it is certainly more benign. But you have something else in your question.
I'm just wondering what the practicalities of this perspective.
Direct capture. Direct capture. So I've lost track of which is first and which is second. Direct capture is first. Direct capture is more competitive with existing systems, which raises the moral hazard problem. I think if you have, on the one hand, and more benign because it is part of the system we know. On the other hand, but you're asking something else. Is direct capture? Oh, I see. I see. Okay. I see. Okay. Feasibility. And energy cost is right up there in the, among the issues that one has to contend with, but it is the case that at the theoretical limit, it costs much less energy to concentrate CO2 even from the dilute 380 parts per million that it starts from, than the energy that is emitted in a power plant. You can also obviously do it with non-renewable. So even if you used a coal plant, you could capture the CO2 back, come out a hit. But you obviously can use non-fossil energy to do the job. But energy is a big feature. The energy of regenerating the absorbers, removing the CO2 from the absorber and regenerating the absorber is a big term and a big cost, a big energy cost and a big dollar cost. The science questions are about the absorption strategy on the one hand and about the collection strategy where the air is blowing over a material in huge quantities of air blowing over. How do you efficiently have the contact between the flowing air and the absorbing material? How do you design that?
Okay.
Good. Prospicience. What can I report? I can report that those who've thought about how sulfate injection might work, much harder than I have, are not at all relaxed about suggesting that we do it now, but rather that we think seriously about an R&D program with field tests and small-scale field tests, all kinds of laboratory development, thinking through the kinds of materials you would use and so forth, and that costs money for an R&D program, competitive with other R&D programs. But the gist of the summer study was what should that look like? What should that research program look like? And over and over again, inserting into this report, we are not saying even that you should do the research without thinking about it further, but surely that you shouldn't deploy at this time. But we're looking ahead. It's possible we'll want to have this capability, and then we might use it. And then that, for some people, that's all about a slippery slope, and nail them down at the beginning and don't let them go anywhere. And indeed, we are so bad at actual execution of almost anything, both because of Murphy's Law and because of our own, cussedness in one way or another, that we're likely to make this a mess. We might as well know it's out there and think it through.
I'd say a word on that as well. I think it's right to say that we've had a lot of failures when we've tried to roll out very large-scale sort of scientific projects. But I think there's two important points to make about that. First of all, we do tend to forget the success stories. So fluoridation of the water would just be one example where people were extremely worried about unforeseen consequences of that. But they did study it beforehand. They decided it was safe, and sure enough, it's turned out that there haven't, as far as we know, there haven't been any kind of catastrophic consequences. But the other thing to say about it is that often when we employ a technology and there isn't a catastrophe, I mean, that doesn't kind of jump out in our memory as being a success story. It's just it's a failure for Murphy's Law, if you like, to take off. So I don't think we should get too carried away with the idea that every time we try to roll out some big technological project and we try to manage the risks properly and we study it properly, that it always goes wrong. I don't think that's really right.
Yes?
Yes. Yes. Yeah, the last part of your question actually took it in a different direction than I thought, because you're saying what will happen to local climates if you invoke this, and that is reminiscent of work that was done on the question of wind harvesting, and does that change the boundary layer as you slow down the winds near the surface? And studies have been made of that. It turns out the atmospheric modeling is not particularly good at it, but the conclusion was that it was going to produce some regional change, but not global change, even if you harvested an enormous amount of wind. But that's the kind of question let me put it this way. Several years, more than a decade ago, I would go to Geophysical Fluid Dynamics Lab and with a pep talk that they were never going to run out of things to do that were related to this agenda of being the evaluators of proposals, many of them crazy, but only after you looked at them for a while. Because that's what they knew how to do, not just to figure out whether the climate was changing, but if we actively intervened in the climate, what was going to happen. So your last question is one I hadn't thought of. What will happen to the climate itself if you pass so much air through fans of some kind or another? You probably don't want to rely on the wind, although these individuals actually disagree about that. But you have a fan. They're adding a lot of change in the atmospheric patterns at low levels. And what does that do to the rest of the climate? Evaporation and downstream and so forth. It strikes me as a rich question. There's one thing I didn't say, and I'm saying, what am I going to feel? In addition to reflecting sunlight, these particles turn direct sunlight into diffuse sunlight by scattering. And the sky becomes less blue. And that is not a small consequence. And I forgot to tell you that.
Okay, poetry mixes in with science. Yes, you were. Bert?
Yes, my question is political.
I mean, and the objectives would be entirely different.
Geoengineering as part of the path solution, that it might fragment and share them off to lose them.
Strikes me as a real concern.
End times. Well, I guess those who subscribe to end times might think that this is all a good thing, right? It's accelerating the second coming. But your point was more that somehow that it's interfering with God's creation. Is that the kind of thought that you imagine?
I hadn't thought through what arguments to have other than intuitive reaction.
Manabi has a question.
Yeah. Yes.
Right. I mean, the model results that I showed are from a model that is actually on the simple side, but it's correct that the average temperature. People have gone quite several steps down this road. They've confirmed that the amount of sulfur you have to put in order to balance against the given amount of warming, and then they're asking at a regional level, how good is the cancellation, how much is the effect on rainfall, and so forth. And in fact, when you cancel, the results that seem to be coming from a number of places are that when the temperatures cancel, the planet gets a little drier than it would otherwise have been, whereas of course global warming gives you a wetter planet. When you cancel it, you get back to zero and then a little drier than before, and there are reasons for that. Yeah, there's a lot of science that's already there to be brought to bear on the problem. We don't want to give the sense that people are ignorant. It's precisely because they know quite a bit that they want to learn more. The science community is saying, let us design some experiments on both the engineering side of it, how do you put, what kinds of particles do you put up and how do you get them there, and what will the responses be. I mentioned briefly in one slide the idea that you could do a little of this and learn a lot about aerosols for the general understanding of the planet, and about this particular scheme, and also have some side effects, such as the stratospheric chemistry, manifest at a small scale. And in the middle of the summer study, I asked the group, would you do that? And most of them said yes. The person who didn't was a true climate modeler, who felt we knew so much less than we ought to know to even do that. The rest of the people were coming from other fields, used to jumping into subjects, and they were more ready to go. I thought that was interesting. Let me mention one thing about what Jorge said, and this will also give you a sense of the subject. Jorge said there'll be a reduction in plant growth. Well, there will be if you cut the wavelengths of sunlight uniformly, but you can reduce the thermal load on the planet in a radiatively selective way There's a certain minimum amount of energy required of incident sunlight to make photosynthesis go. And if you reduce the infrared but not the visible, you could get away with not affecting plant life, at least the photosynthesis part. So that's what I meant by the getting to yes mentality, which is, okay, that's a problem. Is there a way around it? And there are people working on this who are going to follow lines of reasoning like that. Actually, David Keith is a superb example. If it's a problem, let me not just walk away and just try to change it. And that's one of the kinds of people we have as we deal with this class of problems, who has a contribution.
Questions? We have time for one or two more if anybody has any further questions. If not, if we've exhausted the topic, it remains just to thank both our speakers, Rob Socolow and Bennett Foddy. Thanks very much.